Missing link. Today we will discuss free fall and drag force problems, and I'm going to try to do an ugly British accent. But first, a warm-up. A ball of mass m is dropped from rest and subject to the forces of gravity and a force of air resistance with magnitude F equals kV, where v is the ball's speed and k is a constant. Answer these in terms of m and k and g. What is the ball's initial acceleration, and what is the ball's speed a long time after it is dropped? You have 1 minute. Go. Time is up. At the moment that the ball is dropped, there is no speed for the ball, and so that means that the only force acting is the weight force mg. If the only force acting is mg, the weight force, then the acceleration must be g, or 9.8 or 10 meters per second, when the ball is initially dropped. However, when the ball has enough time to reach a final terminal velocity, then the forces kv and mg balance. So then we set kv equal to mg and divide by the speed v to get mg over k, the terminal velocity of the ball. Now for the overview of the lesson. Today we're going to discuss the steps to solving a drag force problem and apply these steps to two different drag force problems. And we're going to draw graphs of the motion of an object that is subject to an air-resistant force. And now for the rules. In each round, you will create a chain of 8 correct mathematical steps. Get your step wrong, and you are the missing link. Goodbye. Here are the chain of steps. First, you will draw a free body diagram to represent the forces of the situation. Then you will write a Newton's second law equation based on the free body diagram. Then you will change the acceleration into the derivative velocity dv dt. Then you will separate the variables v and dv on one side and dt on the other in order to solve the differential equation. You'll integrate both sides, and don't forget to put the plus c on the side with t. If you forget, then you are the missing link. Goodbye. You will solve for the velocity, getting v by itself, but there will be a c still on the right side of the equation. So use the initial conditions to solve for the constant c, and then rewrite the velocity equation as a function of time after plugging in the c. Get one step wrong, and you break the chain and screw up the entire answer at the end. Now let's play the missing link. A space shuttle of mass m lands on a runway. At time equals 0, the space shuttle has rightward velocity v0 and deploys its parachute, causing a leftward drag force of magnitude kv to act on the space shuttle and parachute system. The space shuttle coasts to a stop. Derive an expression for the speed of the space shuttle in terms of time, or as a function of time, v of t, in terms of time, and m and g and k. Follow all 8 steps. You have 4 minutes. Go. is time to see who is the missing link. Step 1, draw a free body diagram. If the space shuttle is coasting to the right, then it would have a normal and weight force which balance and the drag force acting opposite to the velocity. Then we write a Newton's second law equation, kV equals ma. But it is important to remember that the kV is negative because the force from the air resistance is opposite the direction of the velocity. So if the velocity is to the right, the force is to the left. The negative is important. If you did not put the negative, then you are the missing link. Goodbye. Now we change acceleration into dv dt because acceleration is the derivative of velocity. And now we have a differential equation with v, t, and constants. We do algebra in order to get the v and the dv together. We divide v down underneath the dv and move all the other symbols to the other side. So now we have dv divided by v on one side and t with constants on the other side, except that should be a dt. So it looks like I'm the missing link, but I can't say goodbye because I'm being paid for this. So now we're going to integrate both sides. Oh, now it turns into dt. There you go. It was hiding somewhere. Okay, we integrate both sides. The dv over v, the integral is natural log of v. And the integral of a constant times dt is just the same constant times t plus an integration constant. The integration constant is important. Do not forget it. Now, raise both sides to e to both sides to get rid of the natural log. So v equals a new constant, which is not the same as the other constant, e to the minus k over m times t. However, we do not know what the constant is unless we apply initial conditions. The initial conditions are that the speed was v naught at time equals 0. So we plug in the speed v naught into where v is. We plug in the time of 0. E to the 0 is 1. So we get v naught is equal to c, or the constant of integration is just v naught. So plugging in v naught for v and 0 for t tells us that the constant is just v naught. So we end up with v equals v naught e to the minus k over m times t. That is the velocity of the space shuttle as it coasts to rest under the influence of only a drag force. This is an animation showing a block that represents the space shuttle. Notice how the kV force decreases as the speed decreases. That means that the acceleration becomes less and less. So on the acceleration graph, the acceleration is negative because the acceleration is to the left in the same direction as kV. And the acceleration becomes less as the force becomes less, as the velocity becomes less. The velocity decreases exponentially, approaching 0, just as the acceleration does. But the acceleration, or the velocity, is forward. So since the velocity is forward, it is positive. And the position graph is also an exponential, but it rises to an asymptote as the object asymptotically approaches a final distance. So when an object is being slowed to rest by a drag force, it has a limited distance it can go and asymptotically approach that distance. All right, round 2. A ball of mass m is dropped from rest and falls through the air. The ball is subject to gravity and the force of air resistance with magnitude kV, where k is constant. Derive an expression for v, a function of t, the velocity of the ball as a function of time, where down is positive. Your answer will have t as well as m, g, and k as constants. This one is a little bit more difficult algebraically and may require the use of integration by substitution. So because it's a little bit more difficult, you're going to get 5 minutes for this one. 5 minutes to create a chain of 8 correct steps while I glare at you over the internet and post-apocalyptic music plays that becomes more intense as time runs out. Ready? Go. Time is up. Step 1, draw a free body diagram that describes the forces acting on the object. In this case, the force of gravity is down and the air resistance force is upward. So we draw mg pointing down and kv pointing up. Because the ball moves down, we let down be the positive direction. So we write a Newton's second law equation, step 2, mg, the force helping the ball fall, minus kv, the force opposing the ball's fall, equals ma. The force that helps the motion minus the force that opposes the motion equals ma. That is Newton's second law. Then we change acceleration into dv dt. Because acceleration is the derivative of velocity with respect to time, making a differential equation that we can solve to obtain velocity as a function of time. Now comes the tricky part. In order to separate the variables, we now have to take the entire left-hand side and cross-multiply it down into the denominator of the right-hand side. So mg minus kv is going to divide down the entire thing underneath dv. And we will move the dt up so it's on a side by itself on the left. So we see dt on the left by itself is equal to mdv on the top divided by mg minus kv on the bottom. We would like to integrate both sides, but the only way to integrate the right-hand side is for the numerator to exactly be the derivative of the denominator. If the numerator is the exact derivative of the denominator, then the right-hand side becomes natural log of the denominator. mdv is not the derivative of mg minus kv. However, negative kdv is the derivative of mg minus kv. So we need to move this m down underneath the dt, divide it down, and then multiply both sides by negative k. So now we have moved the m down in the denominator with dt and multiply both sides by negative k. By multiplying by negative k, the numerator is now the exact derivative of the denominator. If you were to be doing integration by substitution, then you would let u be mg minus kv, du would be negative k dv, so you would get du in the numerator and u in the denominator. The integral of du is natural log u. So we now step whatever which one we're on, we're going to integrate both sides. So we integrate negative k over m, a constant, times dt becomes the same constant, negative k over m, times t, plus a new integration constant. If you forget the integration constant, then you are the missing link. Goodbye. Now, on the right-hand side, the integral of du over u is natural log u. So we get the natural log of what was in the denominator, mg minus kv. Now, we raise both sides, e raised to both sides, in order to get rid of the natural log. So now we have mg minus kv without its logarithm is equal to e to the minus k over mt. But a plus c becomes a times c when you raise something to the e power, or raise e to the something power. So this plus c becomes a different number times c, but we don't know what the number is, so it doesn't matter. Okay, so now what we need to do is we need to solve for the constant. So how do we solve for the constant? We plug in initial conditions. We know that the ball is dropped from rest at time equals 0. So we plug in velocity 0, time 0, and we get the integration constant at this step is mg. So we plug that back in. The integration constant is mg. So then we solve for v. We subtract over the mg. So mg minus kv equals mg e to the negative k over mt becomes kv equals mg minus mg e to the minus k over mt. However, if we would like, we can dress this up by factoring out the mg. We can make this look prettier, and then we can divide by the constant k to get v equals mg over k times 1 minus e to the minus k over m times t. This function, 1 minus e to the minus constant t, is a function that starts at 0 and asymptotically approaches 1. So then the velocity is going to start at 0 and asymptotically approach mg over kv, or mg over k. Mg over k is the final terminal velocity of a falling ball. As you can see here in this animation, the velocity starts increasing immediately because the only force acting is gravity. The initial slope of this graph is 9.8 or 10 meters per second squared. That is the initial acceleration. But then, as the kV force becomes stronger and stronger, the velocity no longer increases at 9.8 meters per second squared, but its increase becomes less and less and less. The velocity asymptotically reaches mg over k, the terminal velocity. You can see here in the animation the motion diagram of dots and how the dots become equally spaced apart after a long time of the ball being allowed to fall. The ball asymptotically approaches a constant velocity. In the position versus time graph, we start with a parabola, just as we would if this ball was falling with no air resistance. However, as the velocity quits speeding up and reaches a constant velocity, then the position graph becomes a straight line. A velocity graph is a flat line for constant velocity. A position graph is a straight line for constant velocity. So the position graph is asymptotically reaching a straight slanted line representing the final constant velocity of the ball. And the acceleration, which is initially 9.8, asymptotically decreases, asymptotically approaching zero as the forces reach a point where they balance. Okay, time for the bonus round. In the bonus round, I will show you a graph of velocity versus time and then change the situation on you and ask you to draw a new graph of velocity versus time based on the new different situation. So get your pens and pencils ready to draw velocity versus time graphs that I'm about to show you. And let's play the missing link. This is a graph of velocity versus time for a ball falling through the air from rest. Recall that we are treating down as positive. What would this graph look like if the ball were thrown downward with an initial speed that's half its terminal velocity? Time is up. The correct answer appears as this red graph. The velocity starts at half of the terminal velocity, but then asymptotically reaches the same final terminal velocity. Note that the graph always has the same concavity. It does not change concavity at any time. Question 2. What would the graph look like if the ball were thrown downward, but with a speed twice its terminal velocity? You have 1 minute. Now notice the graph begins at 2 times the terminal velocity and again asymptotically approaches the terminal velocity. In this case, the ball is falling faster than terminal velocity, so it will slow down, asymptotically slowing down to its terminal velocity. If the ball is initially moving slower than terminal velocity, it will speed up to terminal velocity. If the ball is moving faster than terminal velocity, it will slow down to terminal velocity. Question 3. What would the graph look like if the ball is thrown upward with an initial speed equal to its terminal velocity? Recall that upward is considered negative on this graph. You have 1 minute. Time is up. The correct graph appears like this. Yes, it is the same shape. The graph begins at negative VT because negative is the direction that we assign to up, or the sign that we assign to up. The ball slows down very rapidly, reaching a maximum height, and then begins its free fall with decreasing acceleration because of the effects of air resistance. So the ball begins with much greater downward acceleration than gravity, slows to a stop very quickly, and then speeds up with decreasing acceleration as it approaches the terminal velocity again. So no matter how the ball's initial motion is projected, the graph of velocity versus time will be a curve with the same concavity everywhere that asymptotically approaches the terminal downward velocity. If you got all these correct, then congratulations, you are not the missing link. All right, do not forget the 8 steps to solving a drag or air resistance problem. Draw a free body diagram. Write Newton's second law, the force helping minus the force against acceleration equals ma. Then change acceleration into dv dt in order to make it a differential equation with v in terms of t. Then separate the v's and dv's to one side and the dt's to the other using basic algebra steps. Integrate both sides. You should have a natural log on the side with v and a plus c on the side with t. Then solve for v so that you get v equals something that involves e raised to negative a constant and a time. Then use the initial conditions of the problem to solve for the integration constant c and rewrite your velocity function after plugging in the value of c. Here are some additional problems for you to consider. All the problems come from the AP Physics C Mechanics exam. So each year is indicated along with the question number. While the entire problem might not have to do with air resistance, some parts of those problems involve the air resistance concept. So take a picture of it with your phone or freeze if you're watching the rewatch. All right, that's going to do it for today. Thank you for tuning in to this episode of The Missing Link, and I will see you next time. Goodbye.